So we will continue where we left off in the last lecture. In the last lecture, we understood the architecture of detection transformer. Today, we will be coding a detection transformer almost from scratch. I will tell you why I say almost from scratch. What's the difference? But before we go ahead and code the detection transformer, I want to do a quick recap so that in case you don't remember the architecture, we will just quickly go through the architecture once. So all the models we discussed before detection transformer, vision transformer, data efficient image transformer, and even the code implementation of Swin Transformer, they were all for classification. We did not do anything for detection, but here is the first time we are implementing something for object detection. So drawing bounding boxes. So detection transformer, roughly, you can think that it has four parts. Part one is a ResNet 50 or ResNet 18 backbone. So it will be a pre-trained neural network. And this ResNet will extract features from your image. So feature map will have multiple channels. So it won't be RGB. It will have multiple channels in the Z stack, but its spatial dimension might be much smaller than the input image. Input image will simply have three channels, RGB. Once the feature map is available, feature map is projected, flattened and projected into the dimensionality of the input embeddings. So if the dimensionality of this one is 256 and the channel number of channels here are 64, you will have to project from 64 dimensional space to 256 dimensions. But basically what you will do is you will construct a sequence of these feature map in as sequence of input tokens. Then those tokens are passed just like how we pass tokens into a transformer architecture in text. Here we pass it through the transformer encoder, and we had gone into the details of the encoder. Encoder will involve something like this. Something like this. There will be layer normalization followed by multi-head attention. There is residual connection. Then again, layer normalization, multi-layer perceptron, and residual. So same architecture. The only nuance was there in the position embedding. I don't want to go into the details of position encoding or position embedding right now, that we have discussed in detail in the last lecture. But in today's implementation, we will simplify it a little bit so that the implementation is slightly easier. The second aspect is once we have the context vectors from the transformer encoder, these context vectors, the number of these context vectors are same as the number of these input tokens in the sequence. So if there are, let's say, 300 individual feature map grid cells that we extracted from the image, you will have 300 tokens in the sequence. Then we move on to part 3 of the detection transformer, which is a transformer decoder. So decoder will have, vaguely speaking, two types of inputs. One set of input is a sequence called object queries. The number of object queries should be equal to the total number of, or the maximum number of rectangles, bounding rectangles that we want to predict. So if the maximum number of rectangles we are interested in predicting is 4, we simply need 4 object queries. So the number of object queries and number of tokens in your token sequence from the context vectors, they need not be the same. In detection transformer paper, they kept the total number of object queries as 100. So that maximum 100 objects you can predict. So first, a self-attention is constructed where these object queries themselves are projected into query key value space. So that was shown in this image. So first a self-attention is constructed. Let me delete a few things from this. So for this self-attention is constructed so that you can create attention maps between tokens within the object queries. So here query key values are produced from the object queries themselves. But for cross attention, query is produced from the object queries, but key and value are produced from the context vectors resulting from the transformer encoder output. And then same thing, you have layer normalization followed by multi-layer perceptron. So at the end of this transformer decoder, what you get is, and by the way, there are multiple transformer decoder blocks in the transformer decoder and multiple transformer encoder blocks in the transformer encoder. So there are different number of blocks. So we have to explicitly mention how many blocks do we have. Within each block, we have to explicitly mention how many number of heads are there in the multi-head attention, etc. So speaking about the self-attention part here, the reason why it was called as self-attention was because the object queries projected into query key value space, they were those the sequence which resulted in producing the query was the same sequence which resulted in producing the keys. So that's why it's called self-attention. Here it's called cross-attention because the sequence which resulted in producing the queries and sequence which resulted in producing the keys are two different sequences. Queries were produced from the object query sequence. Keys were produced from the context vector sequence. Context vector sequence came from the transformer encoder output. So that's why this is called cross-attention, because the sequence, the two different sequences are paying attention to each other. But at the end of all of this, what results is a set of context vectors. And just to refresh your memory, can you comment in the chat how many context vectors will we have at the end? The number of context vectors will be equal to what at the end of transformer decoder? It should be equal to 100, or it should be equal to total number of object queries. It should not be equal to total number of input sequence from the feature map, right? It's dependent on total object queries. And then these context vectors are now converted into class prediction or bounding box prediction. So that is what's shown here. So the object queries converted into context vectors can be used, can be fed through two different multilayer perceptrons. One multilayer perceptron for predicting the class and probability score. One multilayer perceptron for predicting where exactly should the bounding box be. So totally, if there are 4 object queries, maximum number of bounding boxes we can expect is 4. So each bounding box is characterized by 4 parameters: the centroid x and y coordinate, the width and height. Everything will be normalized. So all the numbers will be between 0 and 1. Now, sometimes it may so happen that some boxes predict no object. In that case, in detection transformer, they also define something called as null object, phi. So it's not the case that every single box that the detection transformer predict is mapped into a ground truth box inside the image. Some boxes will be mapped to the ground truth boxes during training, but some boxes will have such low confidence score that it is mapped to it is mapped to null object. And we also discussed something about this mapping, because if the ground truth has, let's say, 5 boxes, and if you are predicting 7 boxes because of your 7 object queries, for example, how do you map 7 boxes to 5 ground truth boxes? You will say you have 5 ground truth boxes plus 2 null boxes. So you have total 7 boxes in the ground truth. You have 7 boxes in the prediction. You try to create the mapping between those two using what algorithm? We had discussed one specific algorithm in the last lecture, if you can mention. How do you match? We match using the Hungarian matching. In Hungarian matching, we discussed about how, using an example, how you can create an optimum score. So the example that we picked was this. There were 4 people who were looking for jobs. There were 4 jobs available. And I am a contractor. I want to distribute the jobs to these workers such that my cost is minimized. Now, each worker proposes different cost for different job, and one worker can only work in one job. So this is where Hungarian matching comes into picture, where I want to optimize the cost. So same thing applies here. So you have predicted boxes, you have bunch of predicted boxes, and you have bunch of ground truth boxes, and you have to construct some sort of, let's say, some sort of loss or some sort of score such that you have to identify the matching between ground truth and predicted boxes to minimize the total loss score. We also discussed about the loss function used in detection transformer. The loss function had 3 components. Let me delete this so that I'm cleaning up this a little bit. The 3 components were, in fact, 2 components. If you look at it from a broader overview. So detection transformer loss consists of loss happening due to classification error and loss happening due to localization error. Loss due to classification error is when I say a dog is a cat. That is an error due to wrong classification. Loss happening due to localization issue is when you say that I have a dog and here is the location, but you are predicting the location wrong. You are not having the closest bounding box predictions compared to where the ground truth box is. So there will be localization loss, and there itself we discussed about 2 losses, L1 loss and global generalized IOU loss. L1 loss was simply modulus of predicted width minus actual width plus modulus of predicted height minus actual height plus modulus of predicted x minus actual x, which is the centroid, plus modulus of y cap minus y, which is the y coordinate of the centroid. This was the L1 loss. And generalized IOU loss was done to prevent something like this. So we discussed two cases, and case 1 and case 2. So let's say you have ground truth box like this and prediction like this, and ground truth like this and prediction like this. In both cases, intersection over union, the vanilla IOU parameter is 0 because intersection area between the ground truth and prediction is 0 in both cases. However, we know that case 1 is better than case 2 because in case 1, at least even in IOU being 0, the boxes are slightly close to each other. In case 2, they are very far from each other. So this is where we constructed something called generalized IOU, where we said we will draw another box, which is the smallest box that encloses both of these boxes. And based on this, we can construct a formula like generalized IOU equal to IOU minus 1 plus P union G, which is prediction union ground truth divided by C. C is the big rectangle which encloses both of these boxes. And based on this formula, we can construct generalized IOU. And we also discuss why the generalized IOU for this case is better than this case, right? So this is where and then we also implemented a simple inferencing on a detection transformer, pre-trained detection transformer we downloaded from Facebook. So this is where we ended last lecture. Now, what we are going to do today is something simple. I had mentioned in the last lecture that training the detection transformer from scratch is difficult. So that is still true. If you read the detection transformer paper, you will realize that training requires a lot of time. But what we are going to do is we'll simplify everything. We will define the detection transformer from scratch, but we will not train it from scratch, but rather we will import pre-trained weights from Facebook so that we will get the experience of coding it, but we will not experience the pain of having to train it for a long number of hours. So within the lecture duration itself, we can try implementing the detection transformer that we coded with pre-trained weights. Now, one thing you have to note here is the pre-trained weights are being imported with certain variable names. So you should follow the exact same variable names for your code to work. So when you are coding along with me, I would like it if you are using the exact same variable names because the pre-trained model has certain parameter names and we don't want to change that. So now what we can do is we can open a Google Colab notebook, empty notebook, and we can start coding. So please get ready with your Google Colab notebook. So there are a bunch of things that first we have to define. As always, we have to define imports. Then we have to define a detection transformer class for defining the whole detection transformer. And detection transformer is actually easy because if you think about it, there is just there is just ResNet backbone, transformer encoder, transformer decoder. The parts that may be tricky will be position encoding that we will simplify. And here, in fact, we don't have to. Okay, there is a question: how will we know the parameters of pre-trained model? We can print it if we want to, but the parameters we are importing from a saving point which is available from Facebook. So, but if you want to see the parameters, we can. I think there are options to print it. But basically, those number of parameters will be very high, right? The question is, what are the variable names of the pre-trained model? That also we can know from the documentation of Facebook. Okay, so first we will define imports. Then we will define a class for writing the detection transformer. Then we will need a code block for loading pre-trained weights. Then we will load the Coco dataset classes because the pre-training has happened on Coco dataset. So if there are 91 or something classes, we will load Coco dataset classes plus some colors that we can use while drawing the bounding box. So colors for bounding box. And we need a function. We need to define a function for scaling the B box coordinates because the by default, the predicted bounding box coordinates will be between 0 to 1. But we can't use 0 to 1 because we need to finally show the bounding box inside our image. And image has certain dimensions, width and height. So we have to scale this from 0 to 1 to WH scale, right? So that for that we'll need a function. Then we will need another function for predicting the function, or another block rather, for predicting the output or outputs for a given input image. And how do we get the input image in the first place? We will need another block of code for defining the input image, and then finally plotting the results. Basically, what does this mean? Overlaying image plus bounding box plus predicted class plus confidence score. So these are the 4 things that we'll display. So now we have to write these many things. I'll do one thing. I will share the link to this collab notebook so that you can write it yourself. But if in case if you face any issue, you can refer to my code directly. All right, so let's start with the imports. So as always, we import torch, PyTorch, import torch, then import matplotlib.pyplot as PLT for plotting images. Then from below, we import image. This is for reading images. Then from torch, import NN so that we can use NN.module. Then we should also import the ResNet 50 or any ResNet architecture. So the backbone that we are going to use today is ResNet 50. So from torch vision.models, import ResNet 50. So this is what we will define as the backbone. Then import torch vision.transforms as T. We were using this to perform certain transformations like from pillow format into tensor format and so on. And import requests, this we will need later. And that's it. I don't think. And one more thing which we can do is, since we are not training the model here, we are only defining and loading the pre-trained models. We can speed up the whole code by not storing any gradients. Like so we can simply set PyTorch to not store any gradients. So set grad enabled false. We can try without this line also, but let's keep it for now. So these are all the imports. So let me just add a text saying imports. Then just run the block of code to make sure there is no syntax issue or some minor issues which you are overlooking. Now we will code probably the difficult part. The difficult part is coding the detection transformer class. So, okay, there is some issue here. Cannot import image from PIL. From PIL import image because this should be capital letter. Thank you. Yeah, because gradients we will need. The reason why we are not storing gradients is we are not performing training here, because if we were to do training, it's very slow because detection transformer requires very long training schedules. So in this case, we are only using the model. We are defining the model. We are using pre-trained weights, and then we are directly using it for inferencing. We are not fine-tuning also. If we were also doing fine-tuning, we will not set this to be false. Okay. So here it's pure inferencing, but still we are writing it from scratch. So we get the best of both worlds. We get the experience of writing the model from scratch, but we don't wait long number of hours for the training to finish. Now we will write detection transformer class definition. Okay, so now let's start with class DETR. We can call it as demo class because we are just, this is not the exact original detection transformer class. There are few differences with respect to position, embedding, etc. And here we will require nn.module so that we inherit properties from the nn.module parent class. then define underscore underscore init. We define the init constructor, and we have to pass a bunch of parameters here. Of course, one of the most common parameters is self. Rest we will write in a moment. We also have to call the init constructor from our parent. So super dot underscore underscore init underscore underscore for the initiation of the init, for calling the init constructor of the parent class. Here we should pass a bunch of things. So first is number of classes. Whatever is the number of classes in Coco, we should pass that here. I think it was 91. So we can just pass it here itself. So our model, our object detection model will be able to detect those objects belonging to one of these 91 categories. It won't be able to predict any other new classes. Then whatever is the hidden dimension. So hidden dimension, we will keep it 256. So for us to be consistent with the implementation of this particular pre-trained model that we are writing. So this is the hidden dimension in the encoder as well as in the decoder. So hidden dimension of the sequence of tokens in encoder, hidden dimension of sequence of context vectors in encoder, as well as the object queries in encoder. Then number of attention heads, n heads, equal to 8 as per the implementation of pre-trained model. So this is the number of heads in the multi-head attention. Then we need to define how many blocks of encoder and how many blocks of decoder are there in the encoder as well as decoder. So blocks meaning how many layers are there in series. These attention heads are actually in parallel. These attention heads are part of a multi-head attention. So every attention head will be 8 attention heads in parallel. But in encoder blocks, in encoder part, there are encoder blocks in series. In the decoder part, there are decoder blocks in series. So we can define that. So number of encoder layers equal to 6. And same for decoder. So we'll say number of decoder layers is also equal to 6. So I think that's all the parameters we have defined here. Now we have to create three things actually. First is ResNet backbone. Then second is defining the transformer with encoder plus decoder. Third is we should have the MLP for class and MLP for bounding box, B box. So these are the three things now we will define. So first, let us start with ResNet. ResNet part is easy. Self.backbone. So backbone is the variable name that we are using. And here we have already imported ResNet 50. So copy this and call the ResNet here. So we are saying our backbone is going to be ResNet 50. Now I have one question here. When we are using ResNet 50 here, is this ResNet 50 pre-trained or not? The one which we just defined. Is it a pre-trained ResNet or is it not a pre-trained ResNet? Okay, all of you are saying it's a pre-trained ResNet. So the ResNet that we just defined is not a pre-trained ResNet. It's just the ResNet architecture. The pre-training will come from the pre-trained weights that we are going to import, right? So when we say we are going to import pre-trained weights of detection transformer, that will include pre-trained weights not just in the encoder and decoder. That will also include the pre-trained weights in the ResNet 50. So here pre-training is not defined. Okay, here it's simply the architecture. Pre-training will be automatically done once we are importing it. So please don't get confused here. So when we define it here, weights are random. So here we just define the backbone structure will resemble that of ResNet 50 architecture. That's all. Okay, and then we have to do one important thing. This ResNet is pre-trained. This ResNet is supposed to be pre-trained on like 1,000 class classification or something like that. So whatever is the last layer, we have to remove it. So del self.backbone dot last fully connected layer, because last layer is meant for classification. Here we are not using ResNet for classification. We are using ResNet just for extracting features. So we can simply remove the last fully connected layer with this line. And then we have to project whatever output we get from ResNet into. So if we go back to our diagram, so this is our this is our diagram. So this ResNet will extract a feature map of certain dimensionality or of certain channel size. We have to project that into 256 dimensions, because here we have defined our embedding dimension to be 256. Where did we define? We defined it over here. So we have to project whatever is the output number of channels coming from our ResNet backbone into 256 dimensions. So the ResNet backbone output dimension here in this particular case happened to be 2048. So we can define a nn.con 2D operation. So nn.con 2D, where this con 2D operation projects from a 2048 channel output at the feature extraction. So ResNet features are extracted such that there are 2048 channels. And this is being projected to hidden underscore dimension using a kernel of size 1 by 1. So we are simply doing a projection using a nn.con 2D. Usually whatever follows nn.con 2D, as we have discussed in this lecture series many times, will be learnable parameter. But this, in the current case, it's not a learnable parameter because we are not going to train on top of it. But initially when we define it, it will appear like a learnable parameter. So here we define the backbone, we remove the last fully connected layer, and then we project whatever output we get from the ResNet, which is in 2048 channels, into 256 dimensions. Then, so now ResNet is done. That's it. So basically, ResNet backbone is very simple. Okay, there are a couple of questions. We are using ResNet for converting input image to tokens. Why can we not use con operations that we have done in the... we are not using ResNet to convert input image. Okay, so ResNet backbone is required because if we directly convert image into tokens, we will be doing what? We will be using patches. Then it will not look like a detection transformer. It will look more like a vision transformer. So detection transformer, one of the best things that they did was they did not shy away from using convolution operation, right? So if we did not use convolution, if we just divided the image into patches and then converted those patches into tokens, we will lose the awesome feature extraction ability that convolution operation brings. So convolution operation is needed here because the filters that are used in convolution has a much higher power of extracting features. And once those features are extracted, use those features to create the tokens instead of using image directly to create the token. So that's the difference between detection transformer and vision transformer. I mean, of course, vision transformer does not have a decoder because vision transformer was meant for classification. So that is also another difference. But that's the idea. Okay. So ResNet backbone we define. Then we remove the last fully connected layer, which was meant for classification. And the layer before that will output something at 2048 channel dimension. And but we don't need 2048 channels. This projection would have been unnecessary if our hidden dimension was also 2048, our input embedding dimension. But input embedding dimension happened to be 256. So you project from 2048 to 256 using nn.con 2D. Here one is the patch size. Now, so that's it. It's easy to define. Now, you may think that transformer part is the most difficult part to define. In fact, it's the easiest in this case because we are not going to define transformer blocks from scratch. Here we can leverage PyTorch. So we'll say self.transformer. This is literally one line equal to nn.transformer. So previously, if you remember, we did not write nn.transformer in any of the architectures. We always wrote nn.multi-head attention. The rest of the things we were writing manually. But here, if we were to write it manually, we'll have to write multi-head attention. We'll have to write nn.sequential so that those, we'll have to write multi-head attention, multi-layer perceptron. We will have to write layer normalization. Then like that, we will define one transformer encoder. Then that encoder we'll have to repeat how many number of times? 6 number of times by using nn.sequential. All of that can be easily avoided by not writing it from scratch. We can use the nn.transformer itself. And this transformer by default, it can accept arguments that define transformer encoder and transformer decoder. We would not have done this if this model only contained a sequence of just one transformer encoder, because then writing the transformer encoder from scratch is easy, just like how we have done in vision transformer or data efficient transformer. So here we will say nn.transformer encoder. So first we have to mention what is a hidden dimension. So hidden dimension we copy paste here. Then we have to mention what is the number of heads in the multi-head attention. Then we have to define what is the number of transformer encoder layers. And then we also have to define how many number of decoder layers are there. So that this is the purpose of these 4 numbers that we define, so that these numbers define our transformer, the whole transformer. When I say whole transformer, I mean both encoder as well as decoder. So now PyTorch will take care of everything that it has to do to define the transformer. That's it, just one line. Now we need 2 lines of code for 2 multi-layer perceptrons, one for predicting the class and probability score, one for predicting the bounding box. So self dot linear classes linear head for classification is nn dot linear. And here we will be projecting. So here, what do we get? First of all, what is the input that goes into this MLP for classification? Can anyone mention the input that goes into? And I'm not talking about input dimension. I'm talking about what is the thing that is the input into nn dot that goes into the multi-layer perceptron. It is some output that comes from transformer decoder, correct? What is the output that comes from transformer decoder? Object query is converted into context vectors. What is the dimensionality of object queries? Dimensionality is the same as the hidden dimension. So at the end of the day, my MLP is basically projecting something from hidden dimension into something, right? Can you tell me what is the projection to? How many classes do we have? Because this is for classification. We have total 91 classes, but actually we have total 91 plus one more class for null object. So we said that detection transformer considers null object also. So number of classes plus 1. So this plus 1 is because detection transformer has null object also. Null object for those boxes without high confidence score. And these are 91 classes in the COCO dataset. Okay, so that is where this variable is being used. Now we can also define self dot linear layer for bounding box. So B box equal to, again, nn dot linear. So here, can you tell me, again, input is coming from the transformer decoder output. Transformer decoder output are the context vectors corresponding to object queries. The dimensionality of those context vectors are all 256, which is a hidden dimension. But what should be the output dimension here? We are projecting from 256 dimensions to what? To 4, because every 256 dimensional context vector corresponding to the object query is used for predicting the bounding box. Bounding box has 4 parameters. So here we will go from hidden dimension to 4. Those 4 parameters are centroid xy, width, and height. Okay, so MLP is done. Now we have to define position embedding. So there are 2 parts where we were adding position embedding. One was position embedding corresponding to sequence of features which we extract from the image. Second was there can be multiple B box. So multiple B box will be there, but every single token is projected into 4-dimensional. But like that, there will be 100 tokens. Why? Because object queries are 100. But if you look at it from the perspective of one token is projected into 4 dimensions, right? Now, position embedding needs to be added for 2 sequences. We have 2 sequences here. One sequence is a sequence of feature tokens. Another is the sequence of object query tokens. So we had two types of position embedding used here. So first is, we can say position embedding for object queries. So position embedding for object queries. So this we can call self dot query position embedding, query underscore pos is equal to, this we will define as a random parameter. So random nn dot parameter torch dot random number, and we need 100 random numbers, and each random number will be of what dimension? Each random number will be of hidden dimension, because the position embedding vector should be of the same dimensionality as that of the input embedding vector. So, and why 100 here? Can anyone explain why do we mention 100 here? Because there are 100 queries, right? There are total 100 queries. and each query should have separate position. In the actual detection transformer paper, if I remember correctly, it was not initialized as random, it was initialized as zeros, but here we are initializing it as random. That is one difference. Next is position embedding for the image feature sequence. So here there is a little bit of complexity. The complexity is that image feature sequence also we can, define something like self dot feature position or something. We could have called this like this. And then nn dot parameter torch dot rand. This will be hidden dimension, but this will be, instead of 100, it will be width of the feature matrix multiplied by height of the feature matrix. We could have done something like this, but that will not give us the information about the fact that you actually have XY. It's a spatial, originally it was a spatial feature matrix, right? So features were extracted from image. There was some spatial information. So if we can somehow preserve that spatial information, that'll be great. So we have to create parameters corresponding to row and corresponding to column separately. So what we do is self dot row embed, we will define, then self dot column embed also we will define. Okay. Now row embed, we will say it's also a parameter, and we will start as a random parameter, and the embedding dimension will be hidden dimension divided by 2. I will say why divide by 2, because we are going to concatenate row and column. So that hidden dimension divided by 2 concatenated with another hidden dimension divided by 2, totally it will become hidden dimension only. So here the dimensionality of this row embedding is hidden dimension divided by 2. But what is this? It's actually not 100. What is this 50? And this should be also torch.rand 50 comma. So what is this 50 number? In fact, this can be 50, this can be 100, etc. It can be anything, but what should this number be ideally, according to you? See, what was this? This 100 was the number of positions that we require in our object queries. Because we had 100 object queries, right? We defined 100 position embeddings. By the same logic, if we are creating row embeddings, here this should actually be number of rows, which means width of our feature matrix, right? And this should ideally be, since this is column embedding, this should be height of our feature embeddings. So that is what we want to define, but we don't know the width and height here where we are defining this, because here this is just a framework. We have to define the forward function to actually know what is the width and what is the height. So what we say is the ResNet 50 model, when it creates this 2048 dimensional or 2048 channel feature matrix, the spatial dimension is something like 42 by 25 or something like that. So any number greater than 42 will work here. So this can be 43 and 43. Because later I can say, yes, I am creating 43 row embeddings and 43 column embeddings, but I don't need 43 column embeddings. I only need 42 column embeddings and 25 row embeddings, because the feature matrix that ResNet 50 outputs will have 2048 channels, but height and width of that is 42 by 25, something around that, which means any number greater than that maximum number of width or maximum number of height you need is good enough. So here, to be safe for ResNet, you can define this to be 50. You can define it to be 100. You can define it to be 500. Anything is fine. But we won't be using all of them. We won't be using all the 50 row embeddings. We won't be using all the 50 column embeddings. We will only use that many row embeddings as there are number of rows. So if there are only 42 rows, we'll only use 42 row embeddings. If there are 25 columns, we will only use the first 25 column embeddings, right? So here the reason why we select 50 is because we want to define a number that is greater than the maximum dimensionality, maximum spatial dimensionality of the ResNet output. Now we want to, but still position embedding is not something of hidden dimension divided by 2. It has to be that of hidden dimension. So somehow we have to use the row embedding and column embedding to create our final position embedding. So what we say is that we can do in the forward pass. But just let me just draw and make this clear for you. So if we have a ResNet backbone, from this backbone, we are extracting something. This something has 2048 channels, but this dimension is 42 and 25, something like this. And we are projecting this into a dimensionality of 256. So this will be 256. Okay. But this will still remain 25, 42. So the total number of tokens that we have in our token sequence of the feature map is only 25 multiplied by 42. But the total number of position embeddings that we have just defined is 50 multiplied by 50. But we don't need this many, but we are defining it to be safe such that we have these many at least token position embeddings available. In the case of position embedding for queries, object queries, we said the number of tokens that we need was 100. The dimensionality of each of those number of position embeddings that we need, vectors that we need was 100. The dimensionality of each of those position embedding vector was 256, which is the embedding dimension. Here also, ideally, we just need 25 by 42. That many, this number, I'm not 100% sure whether this is 25 and 42, but I just know it's less than 50. You can check this. But basically, we just need only these many position embeddings, each with 256 dimensions. That is one requirement. Second requirement is this should not be just a random sequence. The sequence of these position embeddings should somehow encode the fact that you have rows and columns, because there is a 2D nature to this, right? Because this is two-dimensional information. So that is why we define the row position separately and column position separately, so that we can combine those two information to produce sequences which take into account the fact that there is a 2D information here. So position embedding can somehow embed 2D information. So those are the two requirements. And how are we satisfying this requirement? We are satisfying this requirement by saying that I will define 50 row embeddings and 50 column embeddings. So maximum I'll be 2500 I'll define, which is greater than this number. 2D information I'm satisfying by the fact that I'm defining column embedding and row embedding separately, and then I'm later concatenating. Why do we require concatenation? One reason is we want to mix the row and column information, but at the same time, this is defined to be of hidden dimension by 2. This is also defined to be of hidden dimension by 2. But our actual dimensionality will be 256, which is hidden dimension itself. So when you concatenate this and this, you will get hidden dimension by 2 plus hidden dimension by 2. So total dimensionality of your embedding will be 256. So this is what we are doing. All right. Now we can write the forward pass. Okay. So forward pass is where the model will be passing each token. So define forward. And every forward pass usually had two inputs, self and x, where x is the current token. But here we can call this as inputs, self comma inputs. Then I think my indentation is wrong. Yeah. Then first we have to do forward pass through ResNet. So forward pass through ResNet. So here we use different layers of the ResNet separately. So x equal to self dot backbone. So self dot backbone is the ResNet backbone. We had defined self dot backbone here to be ResNet 50. So x equal to self dot backbone dot the dot conv1. Conv1 is the first convolution happening in the ResNet dot input. So this conv1 is defined just by the fact that we are defining the backbone to be ResNet 50. So conv1 is already defined inside ResNet 50. Then we again pass it through the next ResNet layer, self dot backbone dot batch normalization. So first batch normalization in ResNet. So this is part of ResNet structure. Okay, I'm not pulling this out of nowhere. This convolution, this batch normalization is part of the ResNet structure. X equal to self dot backbone. From the backbone, we pull the ReLU for activation function. Then x equal to self dot backbone dot max pooling. So max pooling will reduce the spatial dimensionality of x. And now, so none of these are ResNet blocks. So ResNet has the blocks called residual blocks. Oh, inputs. Yes, thank you. Residual blocks. So none of these have residuals. This is convolution. This is batch normalization, ReLU, max poolings. And now comes the actual ResNet block. So x equal to self dot backbone dot layer 1. So layer 1 is the first ResNet block. Then x equal to self dot backbone dot layer 2 of x. And like this, we will need layer 3 and layer 4. So 4 residual layers. So ResNet 3 and 4. So by the time why can we not do simply self dot backbone of inputs? Because self dot backbone, we are not using every single layer in the ResNet. The ResNet 50 will have 50 layers. So we are not necessarily using everything, right? We are only using it according to what this small pre-trained model was trained on. So we want components from the ResNet, but we don't want the whole ResNet necessarily. I think we are making the ResNet model a little bit smaller by doing this than the original ResNet 50 architecture. And that was maybe done by the people who pre-trained this model to make the pre-training a bit fast. Okay. Then we say we had defined one thing here. We had defined a self.convolution. This convolution was done to project the number of channels, which was 2048, into a hidden dimension, right? So now whatever output we have, we can project into our hidden dimension. So now we say h equal to self.conv of x. So by the time of this layer 4, we will have 2048 channel dimension, and this h will not have 2048 channel dimension. This h will have only 256 channel dimension. So this is the forward pass happening through ResNet, and this is projecting from 2048 to 256 dimensions. And now we have to pass this through transformer. But before passing this through transformer, we have to define the position embedding, right? So now let's extract height and width. So height comma width, because we need to know the height and width of the inputs, so that instead of using all the 50 row embedding and all the 50 column embedding, we can just use how many ever we need. So h comma width equal to h comma shape of the last two dimensions. So -2 means last two. So this will extract the height and width of each of the input feature. Then we say position embedding pos equal to torch.cat. So here is where we try to concatenate row embedding and column embedding, but we have to do a little bit of processing. Processing meaning the dimensionality should match. So first, let's write just what we are trying to do. We want to concatenate self.row embed and self.column embed. However, what we have to do is we don't want the whole of this. We just want for row, we just want everything from 0 to W. For column, we just want the position embeddings. We don't want from 0 to 49. We just want 0 to width. Similarly, for column, we don't want, for column, this should be 0 to width. For row, this should be 0 to height. Correct? Another thing is, this one has only, it had only 2 dimensions, basically. Or rather 3, it had only the number of sequence, basically number of images in the sequence. And it had per image width and height, but batch dimension is absent here. So we have to add a batch dimension at position 0. So what we do is we add unsqueeze of 0, which means an extra 0th index item will be added. to add the batch dimension. So this will increase the dimensionality of this position, I mean, this self.column embed by 1. We have to add that here also. I'll explain this to you once in detail. Let me first write this. And then we have to repeat this position embedding because this is column embedding. So for every single row, as long as the column identity is the same, column embedding can remain the same. Similarly, for every column, as long as row embedding index is same, that value can repeat, right? Because with the row index of 3, maybe there are 6 different columns. With the column index of 5, maybe there are 4 different rows depending on the size of the matrix. So what we can do is we can make this thing repeat a few times. So we do dot repeat of h comma 1 comma 1. So what we are doing here is that this column embedding, we are making it repeat along every single rows. Similarly, a row embedding, we are making it repeat along every single column. So since it is repeated along column 1 comma w comma 1. So what we did here is in this line, we had 50 column embeddings, but we extracted only as many column embeddings as there are number of columns, which is the width. Here we extracted those row embeddings. We did not extract everything till 50. We extracted only from 0 to h because h is the total number of rows because h is the height. So we don't want all the row embeddings from 0 to 50. Then unsqueeze of 0 will add a batch dimension. Dot repeat of h comma 1 comma 1 will ensure that my column embedding is repeating along every single row. Similarly, dot repeat of 1 comma w comma 1 will ensure that my row embedding is repeated through all the columns. And then torch dot concatenate, meaning this whole thing is concatenated with this along which dimension? We can mention the dimension along the last dimension equal to -1. And what is the last dimension? Last dimension is the embedding dimension. Embedding dimension was originally hidden dimension by 2 for this guy and hidden dimension by 2 for this. And when we concatenate two such things, the last dimension of this concatenation will become embedding dimension itself. Okay. And then we do one more thing. So now we have a sequence of, I'll explain this to you once I write the code, sequence of token, which we flatten the height and width dimension and then unsqueeze of 1. So I have written this down because there is a little bit I want to explain. Let me first copy this code and let me go back to my Miro. So let me paste this here. Okay. So this is the code. Okay, so let's now go through this. So what we are using here is this position embedding is added to, okay, actually, let me write one more line of code because I want you to see where the position embedding is added. Then only the position embeddings dimensionality will make sense. Because I hope this part is clear for you, but this you need to see why we are doing this. And for that, I need to write one more line of code. Now, we add the position embedding to the variable h, because h is now the extracted features projected into 256 dimensions. And before we pass this into a transformer, we should add this. So let me write this. H equal to self dot, actually, let me, before passing this, h equal to position embedding plus h dot flatten of 2 dot permute of 201. This also needs explanation, so we can explain both together. So this is one input that goes into the transformer. So the transformer requires two inputs. One is the input corresponding to encoder, and one is input corresponding to decoder, because in the transformer we are defining both encoder and decoder. So the input that goes into encoder is basically the flattened sequence of tokens in the appropriate order. So this order is, the permutation is done for a specific reason, which I'll explain in a moment. But there are two inputs that go into our entire transformer: input corresponding to encoder, input corresponding to decoder. Input that goes into encoder is nothing but the sequence of features that are converted into 256 dimensional space, which is also flattened. But to those features, we are adding the position embedding. So position plus h dot flatten of 2 dot permute of 201, that is one input. Another input that goes into our transformer, not in encoder, but in decoder, is the position embedding corresponding to, is the object queries themselves. So self dot query position dot unsqueeze of 2 of 1 dot, then here we have to call self dot transformer, and then dot transpose of 0, 1. So few things I have to explain here. I have to explain why this transpose is done. I have to explain why this unsqueeze is done. I have to also explain where exactly is the position object. I mean, where exactly is the object queries, because we defined the position embedding for object queries, but where exactly is the object queries themselves. So what we can do is we can simply say that the position embedding corresponding to object query is this. It's, I mean, the object queries are the position embeddings themselves, meaning object queries were, if you remember, in original detection transformer started as 0 vectors. To those 0 vectors, we added learnable position embedding, if you remember. So when you add a 0 vector with a learnable position embedding, effectively that vector is learnable, the learnable position embedding itself, right? So this query position embedding is a learnable parameter. You have 100 such learnable parameters, each of 256 dimension. If you add these 100 vectors to another set of 100 0 vectors, the result is this vector itself. So you just need one vector to start with for the object queries. So here into the transformer, we are passing two inputs. The first input is the input that is supposed to go into the encoder block. Second input is the input that is supposed to go into the decoder block. So decoder input is the object queries themselves, which is equal to, numerically equal to the object query positions. Here they are learnable embeddings. In the actual transformer, in the actual detection transformer, these were actually sinusoidal position embeddings. The position embeddings corresponding to the sequence of object features, they were sinusoidal position embeddings, if you remember the discussion from the last lecture. But here we did not use sinusoidal position embedding. We used a row and column position based position embedding. That's one difference. So we are adding the position embedding to whatever output we get from projecting our 2048 channel output from the ResNet into 256 dimensions. So we are adding position embedding to this. I'm yet to explain these dimensionalities. I'll come to that in a moment. But overall, I hope you understand what this parameter is. Here, effectively, this is the position embedding added with the object query, which is what we are passing into the transformer. And whatever output we get from the transformer, we are transposing for a certain reason. So now with this understanding, now with the fact that this is the line that we are looking at, we can try to go through the reasoning behind, the Python reasoning behind why are we doing this permute operation and transpose operation. There is nothing conceptual there. It's just due to the reason of how Python is representing a few things. So how do I start? Okay, let me start from here. So look at this line of code. In this line of code, we are adding position embedding with h dot flatten of 2 dot permute of 201, which means obviously the dimensionality of this and the dimensionality of this should be the same. So once we understand why the dimension, what are we doing with this h variable, once we understand that first, then we can go back to what we were doing with this position embedding dimensionality. Why were we doing some certain operations that we will easily understand. So first, let us look at this h dot flatten of 2 dot permute of 201. So firstly, what is h? H is the output that we got after we performed this conv operation. We did convolution operation to project our channel dimension from 2048 to 256. Now we have to first ask, initially, what is the dimensionality of this h? The dimensionality of this h is, it has 4 dimensions. First of all, it's a tensor. So h will have a batch dimension, channels, height, and width. So here, if the batch size is 1, number of channels might be 256 because we have transformed. Height will be 25 or 42 or something. So let's keep this 25, and width is 42, something like this, right? So this will be the dimensionality of the variable h. It has 4 items and batch, channels, height, width. Now, when we do the flatten of 2, what we are doing is we are combining the height and width into one single thing, because finally, when we are flattening the whole sequence, we are not keeping the 2D structure. The features which were extracted in 2D should be finally flattened before passing into transformer encoder. See this. This was in 2D. So if this was h and if this was w, h times w, that is the total number of tokens in this sequence here. So we have to combine h and w, which is what we are doing here. So first we say flatten of 2 means everything after second dimension will be combined. So this is 0th dimension, this is first dimension, second dimension is height, third dimension is width. So second and third dimension will be combined. So now h will become something like this. Batch, channels, then width times height. What is width times height? That is the total number of tokens in our input sequence. So that is h dot flatten of 2. Now we do a permute of 201. So permute of 201 means this is 2, this is 1, this is 0. 2 will go here, 0 will go here, 1 will go here. So now the dimensionality will become height times width, comma batch, comma channels. Now look at what this is. Height times width is number of items in the sequence, or sequence length. Batch is basically the batch size. Okay, this part is understood. Channels is the embedding dimension. Now, you might naturally have a confusion that isn't usually batch dimension the 0th dimension? Isn't that what we are supposed to do? So why are we doing dot permute of 201 instead of permute of 0 to 1? Something like, because 2 and 1 should be replaced, or basically transpose of this last dimension and second last dimension. Why are we keeping batch dimension as the dimension number 1 and 0th dimension as the total number of items in the sequence? The reason why this is done is actually in PyTorch transformers, it expects this kind of a structure. You might remember from the vision transformer lecture where we implemented MNIS that when we were defining the multi-head attention, if we did not have this batch first equal to true, if this was not there, we were getting very poor accuracy. That was because by default, there our data set was in such a way that batch was the first dimension. So we had to explicitly tell PyTorch that our first dimension was batch. But if this statement was missing as an argument in the multi-head attention, we were getting wrong responses, because PyTorch will by default expect sequence length to be the 0th dimension. So here we are passing sequence length as the 0th dimension. So now let's look at what is the dimensionality of this at the end of the day. This h dot flatten dot this thing. It will be sequence length, comma, batch, comma, embedding dimension. This is how this looks like, which means if we are adding another vector like position embedding, it should fit this. Now let's see what we are doing with position embedding. Position embedding was this. Let me copy paste it here. I think I have already done. So first step, I hope you already understood. Self dot column embedding of column W. Here we are extracting, instead of all the 50 items, we are only extracting things until W. And okay, so here let's read this. You have a feature map H of shape batch, comma hidden dimension, comma H, comma W, and which we are converting it into a certain shape. I think this part we are already knowing, I think, but we want to know why we are doing this flatten of 0, 1 and dot unsqueezed of 0. So here the dimensionality of this self dot column embedding will be H, comma 1, 1, I think, and dimensionality of this will be 1, W, 1, and this 1 is basically the embedding dimension. So finally, when we concatenate these two, it will look like H, W, embedding dimension. So before we do this dot flatten of 0, 1 and dot unsqueeze of 1, I think the dimensionality, if I'm not wrong, should look something like this. Let me check if there is any mistake. Dot unsqueeze of 0, H, 1, 1, dot unsqueeze of 0. Last dimension is embedding dimension. Then flatten of 0, 1. Yeah. And now when we flatten 0, 1, this will look like these two items will be combined into one single thing. So H times W, comma, embedding dimension. This is what will happen after the flatten of 0, 1. Then after of unsqueeze of 1, one additional dimension will be added. H times W, comma, additional dimension will be added here, comma, embedding dimension. And here batch size, this is basically the batch size, right? So now if you, and this is what, this is the position embedding variable. If you now compare the position embedding variable, H times W is what actually? This is the sequence length, the total number of tokens in our sequence. The second dimension is the batch dimension. Last dimension is embedding dimension. And this one also was expecting something like that. Sequence length, batch size, embedding dimension. So this is the kind of the Python logic why we are performing these operations. But the basic logic, the basic idea is simply the same. You add position embedding to the token sequence before you pass it to transformer encoder. Into the transformer, you pass both the input into the encoder as well as input into the decoder. Okay. So now we will, after this H will transform to whatever output comes out of the transformer decoder, because this transformer is a sequence of encoder and decoder. Now what we can do is, we can say return. I don't think we have defined this thing yet. We said we will define the multi-layer perceptron. Okay, this we are yet to use, but let's come to that in a moment. Now we can return two things. Predicted logits. Why we take transpose? Oh, yes. Great question. I forgot to mention that. So the reason why we take transpose is the transformer encoder output, transformer decoder output will be in this format. Sequence length, batch length, embedding dimension. But in general, for training, for plotting everything, the easiest thing for us once we are outside the transformer, as usual for any tensor, is to have batch here and sequence here. So for that reason, whatever output we get from the transformer, we flip the 0th dimension and first dimension. We transpose the 0th and first dimension so that batch comes back to the 0th dimension once again. So that is what this line does. Dot transpose of 0, 1 means finally this H, after we have the output. So this is now the transformer output. That output we transpose such that batch dimension again comes back to 0, so that late in training, in plotting individual images, etc., we are usually used to batch dimension being first. So we don't have to change the code anywhere else. This is just to take care, this whole exercise is just to take care of the fact that transformer was defined in such a way that sequence length was the 0th dimension. Okay. And here we have to output the predicted logits, and one more thing we have to output is predicted boxes, bounding boxes. So two things we have to output. And how do we output this? Logits are nothing but h converted into something using this linear class. So self.linear class of h. Then, and here also, like in this linear class multi-layer perceptron, it expects batch dimension as the first dimension. Then this will be self.linear box or b box. I forgot the, yeah, linear b box. Self.linear b box of h, but then bounding box coordinates should always be between 0 and 1. So the simple thing which we can do to ensure that this number is between 0 and 1 is pass it through a sigmoid function, so that it will be between 0 and 1. And that's it. There is a question: is the sequence in this is sequence length the data set it needs to give output through weighting of vectors? And is sequence length the data set it needs to give output through weighting of vectors? I'm not understanding the question actually. Could you rephrase it? Are you asking what is the sequence length? If that is the question, sequence length is simply the number of tokens. Number of tokens is basically total number of height multiplied by width of the feature, the feature matrix. Feature matrix has 2048 dimension, but certain height and width. Height multiplied by width is the total, is the sequence length. Features, the channels were 2048, which we project into 256 dimensions. So we implemented three things here in the forward pass through ResNet. Then this was forward pass through the transformer. Let me write it here. Then in the return, there was a forward pass through the MLPs for classification and B-box prediction. So that's all. I think we coded the most difficult part in today's lecture. This is the detection transformer. Let's run to see if there is any basic syntax issue or not. I think it's fine. Okay, so now it's relatively simple from here. So first is using pre-trained weights or importing pre-trained weights. Weights from Facebook. This line of code, it requires a particular URL, but I'll write everything except that URL. I'll just copy paste. So DETR equal to this name, whatever the name was, DETR demo. And nothing we need to pass here. And then state dictionary. This is where we import something from PyTorch. So torch.hub.load state dictionary using URL from _URL. And this is where we have to pass the URL equal to something. And that's all, just URL equal to something. We'll put the URL in a bit. Then once we have this detection transformer dot load _ state dictionary of, and then we pass this here. So this is how we load the pre-trained weights. And then we set the detection transformer to evaluation mode or validation mode. Actually, not even validation mode, just eval mode for inferencing. Now we have to pass this URL from where we can download. I have the URL handy over here. This is the URL. I think that's it. This part is fairly straightforward. Torch has, okay, this should be hub. Okay, so this is the architecture now. You can see the full architecture getting printed, exactly the parameters. I mean, not the parameters, the exact architecture. Okay, so now we can write Coco classes and bounding box colors to be used. There are multiple ways to do this. We don't have to manually define it like this, but anyway, I have it manually defined here. I can simply copy paste the 91 Coco classes, and these are the colors or for the bounding box that we are going to use. So if we have 100, maximum 100 bounding boxes, these 6 colors we will repeat. We will even for different classes. So maybe carrot and toaster may end up, if we have a carrot and toaster in our image, they may end up having the same bounding box color. Okay, so after this, we can now write a function to scale the bounding box from 0 to 1 to image h comma w. So 0 to 1 will be because we use the sigmoid function. If you remember, the default bounding box size will be from 0 to 1 because that's how the bounding boxes are normalized. But we need to now, for plotting purpose, we need to put it back to h comma w scale so that when we are overlaying it on top of the image, the bounding box size is appropriate. I mean, it's corresponding to that of the input size. So first we have to define a transformation. So transform equal to t dot compose. So t we had imported earlier in the import. Then first t dot resize to 800. These are just done for we can use any parameter here. I think even if we don't resize, I don't see any problem. T dot to tensor. This to tensor is done because we want to convert the images from pillow format to tensor format. Then t dot normalize. In this normalization, we pass certain parameters, which are the mean and standard deviation of the data set, which is ImageNet data set that was used for pre-training the ResNet 50 model. So these numbers is already publicly known. If we don't know this, we won't be able to define it explicitly like this, okay? And I think I have an extra bracket, t dot resize. Yeah, I think it's correct. Then define bounding box or box center x, center y, width and height from this format to xy format. xy format meaning the limits of x-axis left-hand side limit, y-axis left-hand side limit, I mean top limit, x-axis right limit, y-axis bottom limit. Define this, and then we say x center, comma y center, comma width, comma height. This is equal. This is already available to us from our x. So x dot unbind of 1, because the bounding box coordinates are already available from the output. This output will give us the bounding box. Actually, let me just remove this. This bounding box coordinate will give us the 4 of the outputs, which is at index 1. So we are just unbinding it so that we have these 4 items separately. Now we say b equal to, here we need to convert these coordinates into xy limits, left-hand side limit and right-hand side limit. So what will be the left-hand side limit? X center minus width by 2 multiplied by 0.5. That will be the left-hand side limit. Then right-hand side limit will be, or the y coordinate lower limit will be y center minus 0.5 multiplied by height. By the same logic, we can define the upper limits. This will be plus. From center, you add half width to reach the right-hand side limit. From center, you add half height to reach the top limit. Top limit or bottom limit, looking at based on the coordinate system. So this is now the bounding box coordinates converted into lower limit and upper limit format. Then we can simply convert this back into a tensor. So torch dot stack b along dimension 1. So here essentially what we are doing is we are converting, here we had created an unbound set of x, y, w, h. Now we have a list of 4 items here. We are converting that into back into a tensor format. Values of b will be between 0 and 1. No, values of b will be between, it can be less than 1, right? Because the minimum value of c, let's say xc is 0. The maximum possible value of w is 1. So the minimum possible value of this guy will be 0 minus 0.5 multiplied by 1. So I think this will be between minus 0.5 and plus 0.5, if I'm not wrong, the values of these numbers. But that's okay, because we are just using, this is not used for calculating any result. We are just using this to for plotting. So once we have this, we can scale this into width and height format. Then we say define rescale bounding boxes, B boxes. And we pass 2 things here, whatever is the output bounding box and whatever is the size of the image. And then we say image width and image height is equal to size. So width and height of the image we have. This is the actual width and height. Then b equal to, then we call this function of output box. So now we pass this output box into this, so that now we get a tensor with bounding box, I think values between minus 0.5 and plus 0.5. Then we say b equal to b times torch dot tensor. Now we are scaling, and we are scaling such that image width and image height has to be used. So image width, first item will be scaled by image width, because this is x coordinate. So image width. Second item will be scaled based on image height, because second item is this y coordinate thing. So image height. We have 4 items total. Third item will be scaled based on image width. Fourth item will be scaled on image height. So this is the x center left hand side coordinate. This is the this is the x left extreme, x right extreme, y left bottom extreme, bottom or top, I have to check, but this is 2 extremes of y scaled by the image height. This is 2 extremes of x scaled by the width. When I say extreme, extreme of what? Extreme of the bounding box, coordinates of the bounding box. Then that's it. And then return b. Just run this to see if everything is okay. Now we can predict the values of bounding box, predict outputs for a given image. So we are yet to pick the image of interest. So predict outputs, define detect, just writing a function for this. We pass the image, we pass the model, we pass the whatever transformation operations that we have defined. Then we say image equal to transform of image dot unsqueeze of 0 to add a bash dimension. Then outputs equal to model of image. And where have we defined the model? Model we have yet to define, or we have defined. Okay, we are yet to define the variable model, but finally this will be the model that we are using. But we'll define it in the next block. Outputs equal to model of image. And now once we have the output, we have to send the boxes. So which boxes? We just care about high probability boxes. So probabilities and the boxes to keep. In rescale B boxes, what is by, where is that? Oh, this was supposed to be B. My bad. I think it automatically, this was supposed to be return B. Thanks. Yeah. Yeah, I hope there is no other mistake automatically crept up, but things look good. Now probabilities are outputs of, so outputs is now storing 2 things, this and this, because these are the 2 things that are being returned from the detection transformer class. So outputs of, what was the first item? predict logits. So this we take outputs of predict logits. Then logits need to be converted to probability. For that, we can use softmax. Then of 0 means we pick the specific, because we have only one image here. So batch size, we just, when we explicitly say batch index 0, we are picking one specific item. Then we need to have every single object query related item. So we have 100 object queries. So we are picking all of them. And corresponding to 100 object queries, we have probability predictions, right? Probability for each object query to be certain object. How many probability predictions do we have? Total probability prediction. So we have 100 boxes. Each of them can be probability predict. I mean, not that. I'm asking about probability. How many classes are there total to be predicted? We have 91 plus 2. 91 plus 1, 92 classes. 91 were the classes in Coco. Last one would be the no object class. So here, no object class, anyway, we don't have to draw anything. We are only drawing 91 rectangles. We are not drawing 92 rectangles maximum, right? So last item we don't need. So here we say pick everything except the last item. So softmax score. So output logits are converted to softmax. And then from that, we pick only the last, everything except the last object class. Because softmax will create a probability score distribution from with index from 0 to 90, 0 to 91. That will be 92 items. But you don't want the last item. Last item was the no object class, right? So you just eliminate it because no object you can't draw. Then you say you don't need all the boxes. You only need high probability boxes. So probas of or dot max of -1. So max of -1 means from the output logits corresponding to object classes, pick the maximum, the one with the maximum value. So let's say I have one rectangle and I have a softmax probability distribution, and with 80% probability, there is one particular class that is dominating. So I'm picking that, but then I have to check if the value of that is greater than some threshold. So I can say 0.6 or 0.7 or something like that. So what we are doing is first we collect all the probabilities except the probability corresponding to no object class. Then we say from the probability distribution, find the maximum probability value. And if that value is greater than 0.7, then I'm happy with drawing a bounding box. Otherwise, I don't want to draw a bounding box. So that is what is done here. And then we say, now we have to scale the bounding box, right? So B boxes underscore scaled equal to rescale. There was a function return, what was the name? Rescale boxes. Into the rescale boxes, we have to pass the output bounding box and the size of the image. So we pass outputs of predicted boxes, right? Pred boxes, I think. Yeah. Because output had two items, predicted logits and predicted boxes. So now logits is now correct. Now if we fix the logits, we only pick certain boxes for predicting. But now we have to pass the box for coordinates of those boxes to rescaling. So outputs of predicted boxes. But among those boxes also, I want to keep only, so batch dimension is 0, but I want to keep only boxes with this index. So this keep is basically the index of those boxes who are predicting a certain object with probability greater than 0.7. So these are now the indices that I want to pick. 0 because I'm again picking the batch dimension. So batch dimension was the 0th dimension, and I'm adding a value called 0, which means I'm looking at one specific item. And keep means I'm saying pass the prediction, the bounding box predictions only for those boxes whose confidence value is above the threshold of 0.7. Otherwise, don't even bother scaling the boxes because we are not going to plot it anyway. And second argument that we had to pass was image size, which is, where is image size? I don't have an image size. I'll have to define it, I think, or im.size. And then B box is scaled. Now in this function, this should return this from the probabilities. Only these indices I need to return, and whatever boxes we get after scaling, return all of them, because the scaling was done only for those boxes whose indices were this. So at the end of this function, it will return the probability distribution for boxes with confidence grade, probability greater than 0.7, and the scaled coordinates of those boxes. Okay, so this was actually not predict output. This was actually predict outputs and then scale the boxes. Keep only high confidence predictions. Okay. Now we are at the last part. Now we just need to upload an inference image. An inference. So here we mentioned the URL of whatever image we have to infer from. And then we say image equal to image.open. This is where the import request is being used. So request.get. Then we are getting from the URL, and stream equal to true. I don't know the importance of having this parameter. We can try without that. .raw. This is just happen to be the syntax. And then scores. So image URL we can define after everything else is working. Then scores comma boxes equal to simply this function detect. And into the detect, I have to pass image. I have to pass the detection transformer model. So model, although we are, this variable we are not defined. We are only defining it here. We are passing the DETR. DETR is defined here. Here, DETR equal to DETR demo. So this is an object corresponding to the DETR demo class, and that is what we are passing here. And one more thing we have to pass, which is transform operation. So transform. This transform was defined earlier. And I can pick some random image. So let me just go to our website and pick something. And since we need only URL, I think it's a very easy thing. I can just right click, copy image address, and then paste it here in the URL, and that's done. And then plotting results. So this is the last part. Basically, we are done. We just need to run the whole code once. So define plot underscore results, then PIL image, whatever image we are passing, probability, and boxes. Size of tensors must match. Okay, let me check what's wrong with this. Dot unsqueeze of. Okay, this is unsqueeze of 1 because we are unsqueezing this dimension. That is one mistake. Okay, I'm not sure if there is any other mistake. I'll try running the whole code once. Okay, seems to be working. Let's move ahead. This is the last block and we are done. Define plot results and plt dot figure. We can mention some figure size. Fig size equal to 16 by 10 or something. And then plt.imshow. And we are showing this image, PIL image, pillow image. Axis plt.get CA. Then now we have to plot certain boxes, meaning we have to display certain boxes over our input image. And how many such boxes are there? We have to do a loop. So for P, which is probability, now we are defining the x min, y min, x max, y max. And for this, comma C is the color of the box in zip of, then we can define all of this inside here, probability, then boxes, this boxes which are box coordinates dot to list. So we are converting the tensor into list. Then we had defined colors somewhere. Where was this? This colors. So here we have only what, 1, 2, 3, 4, 5, 6 colors, but we may need more boxes, right? In the same image, we may have 10 boxes, 20 boxes. So we will need at least that many colors. So let's say colors multiplied by 100. So basically that 6 colors will repeat again and again 100 times. Then we say x dot add patch plt dot rectangle. So these are just syntax corresponding to plotting. We are plotting the rectangle such that x min, y min, then x max minus x min, this is the width, comma y max minus y min, height. Then fill equal to false. The bounding rectangle, we just need the boundary. We don't want to fill any color into the bounding rectangle. Color equal to this variable. So color is C, whatever color is being picked. So color equal to C, and line width of the bounding box equal to 1 or 2 or something. Let's keep it 3. Yeah. Then we say CL equal to P dot argmax of P dot argmax means whatever is the class name is P dot argmax. And then text that we want to display will be like a dynamic text. So dynamic text is, we want the class name. Class name we can pick from this. There are classes here. So the reason why we wrote the class names here is so that we can write it on top of the image. So this is classes of whichever is the argmax, the index corresponding to argmax, and the probability score also. So probability would be P of CL, and we just need 2 decimal points, 0.2 F. So floating point with 2 decimals, and text equal to that. So axis dot text equal to x min. So now we have to define where this text will display on the image. So x min, y min, text comma font size of the text. When we write the class, what should be the font size? Then b box equal to face color. So now this is not the b box. This is just the annotation of this text. So if the class name is, let's say, horse, then we just need to display it. So dict of face color equal to something, yellow or blue or orange. Then alpha, which is the transparency, we can set it to be 0.5, and that's it. Then plt dot axis of plt dot show, and then plot underscore results, which is this function itself, we are calling it. And for that, we need to pass image scores that is defined here, IM scores and boxes. Okay, I think with this, we are fully ready to execute the code entirely. Let's just run it once. Okay, of course, there is some mistake. It's not coming correctly. Some issue is there. Space is not allowed in string formatter. Space, which space? I think I have. Okay, something seems to be working, but not good enough because I was earlier getting much better bounding boxes. So let me reduce this from 0.7 to 0.5. Let's see. Okay, clearly something is wrong. It's not, it's detecting wrong boxes. Let me do one thing. Let me run my other code to make sure if it is getting the same error or not. By the way, did anyone manage to get the code running? Um, or are you facing any issues? I'm sure somewhere I'm messing the way I'm picking the best boxes. Yeah, see here it is really good. Very high confidence scores, tie, person in the background, everything is getting detected, but we are not able to get that same thing here. Let me do one thing. Let me share this code with you and let me know if you are able to run this on some image. And once you are getting correct output, okay. Why don't you try this? Why don't you run the code with your own image, some image, and why don't you paste the image here in the chat with annotation? Just take a screenshot of the image and paste the annotated image here. We can also try Pexel's image or let's say um, animals. Okay, this is a nice cartoon image. Let's see how many copy image or copy image address. Okay. It's completely messed up. This panda is coming as elephant. This is horse. Bird is correct. It's detecting some pictures, but I guess that's because Coco dataset may not have pictures like this. Let's try for pictures that actually look like photos. Okay, how about this? Okay, this is working perfectly. So realistic images are working perfectly because Coco probably had that, but not cartoons, animals, photos. Okay, how about this? Okay, so here some things are working, but bounding box. Okay, I know one issue that might be there. There is a maximum limit for the image size that we can feed to this pre-trained model, 1600 or something. So I cannot feed very high resolution image. I have to pick a bit medium resolution. Maybe that's causing this bounding box issue. Let's see. Okay, this is a, yeah, this is a definitely a low resolution image. Yeah, so this one is working pretty well. So whatever objects Coco dataset had, they are getting. I don't think these deers will be part of the dataset. So please feel free to share the screenshots of whatever object detection classes you are getting. Here I will have to figure out where exactly is the mistake. Most of the things are correct, but I'm not quite certain where is the mistake because the confidence score is a bit low. Also, wrong objects are being detected, but I think that will take time. So I have posted two assignments, I think 2 or 3 days back on Swin Transformer. This is based on the previous lecture. So one was about implementing the transformer for another data set apart from MNIST. Another one was counting the total number of trainable parameters to know the size of the Swin transformer that we have coded. So those are the two assignments. Detection transformer, I have not posted any assignment for the previous lecture because it was more about theory, but I will be posting one hands-on assignment based on today's lecture. So overall, the what we have done in detection transformer is we understood the model, we coded everything except the loss calculation part because we are not training the model, we are only inferencing from a pre-trained weights. But we understood fairly well all the different parts of the transformer itself. Only one thing which we did not do here is Hungarian loss. Even if we were implementing Hungarian loss, we would have used a PyTorch function. We would not have coded it from scratch. So you are not missing out too much there. So this brings us to an end of detection part. Now we are moving on to segmentation from next lecture onwards. So transformers, we have now looked at transformers for text, transformers for images, specifically for classification, transformer for detection. And now we'll move on to transformer for segmentation. So that's the plan. So, okay, I think a couple of people are posting images after detection. Okay, nice. Okay, happy to see that the code is working. So try with different classes also, like not just people, objects, animals, everything. Just try that. But this is good. Happy to see the results. If anyone can figure out what's the issue into the earlier code, that'll be great if you can put it on the Discord. But otherwise, it's fine. I mean, we can figure out in 15 minutes if I sit, I can figure out what's the issue. But right now, if I sit for it, it won't become like a lecture. So thank you so much. We can wind up here. We'll meet again next week. I'll post the assignment corresponding to this lecture on Monday. So please attempt that. I'll not keep a deadline. You can take your time. Thank you so much. See you next week. Have a good rest of the weekend. Bye.